Hello, I'm happy to tell you about our work on the Seesaw algorithm. My name is Mikolas Janota. This is joint work with Antonio Morgado, José Fragoso, and Vasco Manquinho. And what we are doing here is that we have two functions that we're optimizing. One is the cost function that is possible to encode into, let's say, a SAT, MAXSAT, or an ILP solver. And this could, for instance, be a size of a portfolio of solvers. And another function that we have is the Oracle function. What we are not able to encode into the solver is a black box function. And that could, for instance, be a time of this portfolio of solvers on some set of benchmarks. Now, how do we optimize on two functions at once? Because they might go against each other and not always we can optimize them at once. So this is where this Seesaw paradigm comes in. So we imagine that on the left-hand side of the Seesaw, we have the cost and Oracle function on the right-hand side. And now we start by the Seesaw being totally minimized on the left-hand side. So we have the minimal cost by, let's say, placing a child on the left-hand side. And now we put another child on the right-hand side, and that starts to drive the value of the Oracle function down. And now imagine the child starts to eat some cake and keeps on driving the cost of Oracle, so the value of the Oracle function down, until eventually it also hits its minimum. As this is where this name of Seesaw comes in. And the thing that we show here that is under certain conditions, we explore the whole Pareto frontier of these two functions, which is rather interesting because this Oracle function is really a black box function, which we know very little about. So this is my pitch for the talk, and I'm happy to take questions.